Before watching the video, do subscribe my channel and hit the bell notification icon to get the instant updates.
Next, we'll start with the preparation methods of alcohols. Now, the first preparation is similar to what we had discussed in alkyl halide. If I want to convert an alkyl halide into alcohol, I'll use alkaline hydrolysis, that is aqueous KOH. Hence, the first preparation method is by alkaline hydrolysis of alkyl halides, RX. And the well-known general reaction is RX plus aqueous KOH on boiling gives you ROH and KX. And here the mechanism followed is KOH will break down as plus and minus. The X as a good living group would be substituted by OH minus, giving you alcohol. Hence, it is an example of a substitution reaction. And the X minus as a nucleophile is substituted, hence it is following NSR, nucleophilic substitution reaction mechanism. The NSR itself is also shortly called SN reaction. Short abbreviation is SN. And within SN, we have already discussed, we have SN1 and SN2, two mechanisms. SN1 was favorable for a bulky tertiary substrate. SN2 was favorable for a non-bulky primary substrate. And rest of the details are already being discussed. Also, the same conversion can also be done by using moist silver oxide, which was to prepare in situ silver hydroxide, AgOH. And contrasting to this, if I use dry silver oxide, the alkyl halide would be converted into an ether. The alkyl halide would be converted into ether. So aqueous KOH gives an alcohol, moist silver oxide gives an alcohol, dry silver oxide gives an ether. Also, in place of aqueous, if I use alcoholic KOH, then the alkyl halide undergoes elimination reaction, the beta elimination reaction, and the product in that case is an alkene. Aqueous KOH gives an alcohol with alkyl halide, but alcoholic KOH gives an alkene. Next, the preparation of alcohol from alkenes. The first part in this is acid catalyzed hydration. Acid catalyzed hydration, meaning addition of water. So if I have a double bond carbon and I add water will break down as plus, minus, OH will be added across the double bond and it will give you OH containing compound, that's alcohol. So simply alcohol is prepared by acid catalyzed hydration. Now why the word acid catalyzed? Water is not so strong electrolyte that it will directly add across a double bond carbon or alkenes. So first we need to use the acid and then we can hydrate it with the water. Let's see how the reaction is done. So I'll take the example of an unsymmetrical alkene, that is propene. The simplest unsymmetrical alkene, propene, that is CH3CH double bond CH2. First we add concentrated sulfuric acid in cold condition. Sulfuric acid always should be written as HOSO3H to make the reaction easy. HOSO3H. Now, whenever with the sulfuric acid we write cold, it means that sulfuric acid is going to break down to give only one H plus. It's a dibasic acid. Cold condition mein we are not supplying enough energy for the second H plus to get dissociated. Hence, in the cold condition, sulfuric acid ka breakdown would always give you one H plus. So the other part is OSO3H minus. Now there is an unsymmetrical alkene added with unsymmetrical reagent. So the addition has to take place according to Markovnikov's rule. Markovnikov's rule states that the negative part goes to the carbon or double bonded carbon having less number of hydrogen atom. या सिंपल वे में मैंने क्या बताया था, प्लस जाएगा ज्यादा के पास, माइनस जाएगा कम के पास. Now with that simple addition, left to right, you get the product as CH3. CH will be bonded with OSO3H and CH3. Now the OSO3H combined D could be written as HSO4. HSO4 is called bisulfate or hydrogen sulfate, and the alkyl which is bonded to it is called isopropyl. Isopropyl. Hence the name of the compound is isopropyl hydrogen sulfate or simply bisulfate. Now these bisulfate are the crystalline compounds which can be hydrated with water. That means added with HOH and the solution is to be boiled. On boiling, this H plus takes away the OSO3H to regenerate sulfuric acid. Hence the H2SO4 is regenerated, plus the OH will be substituting this group, giving you an alcohol, and that's the secondary alcohol, isopropyl alcohol or IUPAC, propane 2-ol. So what we have done over here, we have converted propene into propane 2-ol. Correct? Now, and the moment we see Markovnikov's rule, I had given two important statements for this. First, MR follows your mechanism. MR follows your mechanism, that is electrophilic addition reaction. Secondly, MR generally forms a secondary or a tertiary compound, but not a primary compound. So to prepare a primary compound, we had anti-MR, but there is a problem. Anti-MR is possible only for HBr in presence of H2O2, meaning we can prepare a primary bromides or bromoalkanes, but we can't prepare a primary alcohol. So if my requirement is to convert propene to propane 1-ol, I will not be able to do that directly, but indirectly we can do it. How? First, take propene, convert to a primary bromoalkane. Once we have the halide, aqueous KOH would convert that to an alcohol. So, if the conversion is asked of propene to propane 1-ol, look at this. We have propene CH3, CH double bond CH2, add HBr in presence of H2O2. So, we apply anti-Markovnikov's rule. In the AMR, we get CH3, CH2, CH2, OH. That's we get CH3, CH2, CH2, Br. That's 1 bromopropane. Now the bromide can be converted into alcohol by using aqueous KOH. And here we will get CH3, CH2, CH2, OH, which is propane 1-ol. So this is a two-step conversion with the intermediate formation of a primary bromoalkane. This way we can definitely convert into a primary alcohol, but there is a special reaction which is being given to convert an alkene into a primary alcohol, and the name of the reaction is hydroboration oxidation of alkenes. Hydroboration oxidation of alkenes, and I call it as HBO, hydroboration oxidation. So the main thing about this reaction is HBO is used to convert alkene to a primary alcohol. Here we are not going to directly apply anti-MR, but it is an indirect application of anti-Markovnikov's rule. So let's understand this reaction. The word hydroboration, similar to hydrohalogenation, refers to addition of hydrogen and boron. Hydrogen and boron. Now, which is the simplest hydrogen boron compound? The hydride of boron, that is BH3, borane. So the hydroboration means we are going to add BH3. But as you know, BH3 is unstable and it exists as a dimer V2H6. So whatever reaction we will have, we'll just multiply by 2 to get effectively V2H6 reaction. Okay? Now, the hydroboration would be followed by oxidation, and the oxidation here is done by using H2O2. So we have the peroxide used indirectly in the reaction. Okay? So let's understand the chemistry of this reaction. So I have the same alkene taken over here, propene. BH3 में boron is bonded to 3 hydrogen in a planar geometry, sp2 hybridization. Also, if you look at the boron, there are total of 3 bonds, which means 6 electrons in the valence shell. 6 electrons meaning it is electron deficient. Deficient meaning it will act as a source of electrophile. So, if this is a source of electrophile, it can be considered as a Lewis acid, and since boron is deficient, it will acquire a partial positive, due to which the H will acquire a partial negative. So here, when this bond breaks down, the H will be eliminated as H minus, it will give you a source of hydride. So up to whatever reactions we have done, we had the H as H plus, a proton species was formed. But in the hydroboration, the special reaction, we have the source of hydride, that is H minus. Understand this. In BH3, boron is electron deficient due to presence of 6 electrons in the valence shell, and since it is electron deficient, it will have a partial positive charge, H will have a partial negative charge, hence generating a source of H minus, hydride species. So now, we have alkene added with BH3 and we use a solvent THF, tetrahydrofuran. Now THF solvent is nothing but an ether, cyclic ether compound, and we know ethers are used as good solvents. So BH3 THF combination, now the H minus from here will be added to the double bond, and the addition will take place as per Markovnikov's rule. So here I should not be writing Markovnikov's rule, but what we are applying is actually the Markovnikov's rule. So now the negative part of the reagent goes to that double bond carbon having less number of carbon, normal MR hai. So up H minus will be added here, so the boron will be added here. So now H minus goes here to give you CH3, CH2, CH2, and this entire carbon would be bonded with BH2. Now in borane, all the hydride species are identical. If all are identical, they will keep on adding to the double bond until they are saturated. So the total number of moles of alkene consumed with 3 hydride species would be 3 moles. Hence the reaction takes place in a ratio 3:1. So now when the second hydride comes, again it will attack or add to this carbon and give you this alkyl species. So one H would be lost and this will be twice. The third hydride would again be added and this will be again formed, finally giving you CH3, CH2, CH2, the whole thrice, and B. So you don't have to write the 3-step reaction over here, it's only the direct reaction which is required. So just spot where the hydride is going to be added and then repeat it thrice and write a boron, a simple way. Now let's name the compound. If you see this CH3, CH2, CH2 is N-propyl group, 3N-propyl would be tri-N-propyl, and boron outside refers to a derivative of borane compound. Hence the first step, hydroboration, converts propene into tri-N-propyl borane. Next, this tri-N-propyl bromine would be undergoing oxidation, and as I said, the oxidation is done with peroxide, which can be written as HOOH, O single bond O, and the reaction is carried out in alkaline medium OH minus. Now boron immediately takes away the OH, giving you BOH thrice. If I open the bracket, it is H3BO3, and the boron ka acid is called orthoboric acid. Orthoboric acid. So 3 OH groups required for boron, hence now it will be balanced as 3 moles of peroxide. So the remaining 3 OH goes with the propyl group and it forms CH3, CH2, CH2, OH ka 3 moles, and this is the required primary alcohol, that is propane 1-ol. So what we have done, kids? We have converted propene into propane 1-ol by HBO, hydroboration oxidation. And what we can observe over here, we have not applied the MR directly, but indirect anti-Markovnikov rule is being applied because of the use of hydride species from boron and the hydrogen peroxide for oxidation. In short, the conclusion: if propene is to be converted into propane 2-ol, use acid catalyzed hydration. If propane is to be converted into propane 1-ol, use HBO, hydroboration oxidation. Of course, you can also use this particular sequence which I have given, but that is a well-known reaction. There is no direct attack of H+, it is indirect attack of H+. There is no direct attack of H+, it is in fact H3O+, which attacks the double bonded carbon or alkene. So this is by default H+, aqueous, because in water H+ always exists as hydronium ion. But for convenience, we write the H+. So now the H+ can add across the double bond in 2 ways. When it adds here, this carbon will acquire a positive charge, and carbon pe positive charge, meaning there is a carbocation. So if H bonds over here, this becomes deficient. If H attacks here, this becomes deficient. So when H attacks here, it becomes CH2, and this CH2 acquires a plus charge, giving you what type of carbocation? CH2 matlab primary. So primary milega. When H attacks here, it gives you CH plus, giving you a secondary carbocation. Now, if there is primary and secondary, the yield would be more for a secondary carbocation, because the stability is 3 degree, 2 degree and 1 degree. Hence, this H plus will add to this carbon, giving you CH3, CH, CH3, CH plus and CH3. So that's the secondary carbocation formed as the intermediate of the reaction. Now, if there is a formation of carbocation as the intermediate, and if there is a possibility of getting upgraded, meaning becoming more stable to a tertiary carbocation, it will always try to achieve the higher stability. And this achievement of higher stability is done via rearrangement reaction. Via what? Rearrangement reaction. So now, step 2 mein, this carbocation will try achieving the higher stability by a rearrangement. Now rearrangement का simple मतलब है अदला बदली, मतलब within the species there is just migration of atom or the charge or both of them. So in this carbocation, if I look at the adjacent carbon, if this H shifts or migrates on this carbon, the deficiency of this carbon will be lost. But this H is being given away by this carbon, hence the positive charge comes on this. So it's a simple अदला बदली, exchange हो रहा है. H यहाँ पे गया तो प्लस यहाँ पे आ गया. But इससे हुआ क्या? If you look at the conversion, it gives you CH3, CCH3, CH2, CH3 with a plus here, meaning the secondary carbocation has been upgraded to a tertiary carbocation, meaning it has become more stable, and kinetically the reaction rate and the yield will also increase. Also, why it is becoming more stable? Because for the migration of the H and the plus, it will require some energy. So this species will utilize its energy to convert to tertiary. Thereby in this process, the energy is decreased, stability is increased. Correct? Now this type of rearrangement where the carbocations are being stabilized is referred as hydride shift or a methyl shift. Since here the H has shifted, we refer this reaction as a hydride shift. Hydride shift. Also, it is shifted between the adjacent carbon. We write 1, 2 hydride shift. 1, 2 aju baju. 1, 2 hydride shift. Likewise, we can have a methyl shift, phenyl shift, and also 1,3 shift, 1,4 shift. But those are the details not to be discussed for R level. It will be in higher level. At R level, hydride and methyl and even the phenyl shift is important. Correct? Next, once the carbocation is formed, next there will be attack of nucleophile and the plus and minus will be attracted, giving you a tertiary alcohol, and the tertiary alcohol will be this. So, 3-methyl-butanone on acid catalyzed hydration doesn't give you the expected secondary alcohol, but within the mechanism it upgrades to a tertiary and finally gives you this product as a tertiary pentyl alcohol. That's very important. Correct? Now, when we talk about carbocations, there are few common rearrangements which should always be remembered. For example, if I have CH3CH, CH3CH2 plus, what type of carbocation is it? Primary. So it will try to become stable by undergoing rearrangement, which can either be hydride or a methyl shift. अब कौन सा शिफ्ट होने वाला है उसके लिए जस्ट लुक एट द एडजेसेंट कार्बन, बाजू वाला कार्बन. ना बाजू वाले कार्बन पे H है, शिफ्ट करो. If you shift, the plus will shift here. Now what you observe is there is a formation of a tertiary carbocation, hence we get CH3C, CH3, CH3 plus. The primary has got upgraded to tertiary, has become more stable, and on the arrow we should be writing 1, 2 hydride shift. And next common example we have is CH3C, CH3, CH3, CH2 plus. It's a neopentyl primary carbocation. Now, इसके adjacent carbon पे there is no H, but there is a methyl group. So this methyl can entirely shift on this carbon, and hence the plus will shift on this carbon. अदला बदली है. यहाँ मिथाइल पूरा का पूरा शिफ्ट होगा. अब पूरा शिफ्ट होने पर what we get is CH3C, CH3, CH2. This methyl will bond it to this carbon, so I am writing CH3, and the plus comes over here. Again, primary has got stabilized to tertiary. But now here the methyl shift happened, hence we call this particular rearrangement as a 1,2 methyl shift. 1,2 methyl shift. More example. What type of carbocation is it? Secondary. Now, if the H is shifted here, the plus will be shifted here, it gives you a tertiary carbocation. So obviously the hydride shift is going to happen over here. If you do the methyl wala shift, the plus will shift on CH, again giving you a secondary. Correct? So now here which shift is going to be favorable? The hydride shift. Correct? Also observe this CH plus with respect to the single bonded carbon is a secondary alkyl carbocation. But the moment you do the hydride shift over here and the plus shifts here, it is actually converted to a benzyl carbocation. and the benzyl carbocation, if you see, is stabilized by resonance. So this is far more stable as compared to this particular carbocation. In fact, if we have a secondary alkyl, secondary allyl and a secondary benzyl, most stable carbocation is going to be the benzyl secondary, allyl secondary and alkyl secondary, because benzyl and allyl have the stabilization by resonance, alkyl have the stability only by inductive effect. Clear?